So, towards that end, would you look at tonight's homework, boxes 7 and 8. And we're going to do one together, get the process. You're going to try one on your own and further get the process. The idea is to find the area under a curve using infinite rectangles. In 44 number 7, the region was 0 to 4. Okay, so you've got this region, and you're going to use infinite rectangles to find it. Are you with me? I will clarify the ideas and also show you what I want to see. I would like you to start something like this. I know that the area can be first approximated by a bunch of rectangles. The base of each rectangle is a change in x, side to side. The delta x represents bases. The heights of the rectangles are the function at different points. That's what that f at incremental x's is about. So you're looking at sums of bases times heights right there. Do you see? 10, 4. Now, I'm going to put in delta x. Delta x is the base. Now I know the total region is how wide? 4, and I'm going to divide it, instead of 5 chunks or 2 chunks, I'm going to divide it into some unspecified number of chunks, n. Therefore, the base will be 4 over n. So 4 comes from the region width you're given. The n is always going to be there. You're going to divide it into some undetermined number of chunks. Now, the function value, think of it like this. You don't need to draw this picture, but just so we're clear. You've got a region from 0 to 4, and you're gradually going over a 4 over n, then 2 4 over n's, then 3 4 over n's, and so on. And so the heights will be the result of putting those points into the function and seeing what the y is. So with me? So the y, or the function, or the heights, will be the result of putting some number of 4 over n's into the function. All right? As far as the indices here, I is how many rectangles we've gone over, or how many bases we've gone over. Because we're using right, the first height will be drawn at the first 4 over n. So I is going to start at 1. And because we're using n rectangles, the last height will be the nth 4 over n. And if you think about what that would look like, the nth 4 over n would be the nth 4 over n would be the n's cancel, and you just have f of 4, which is the far right side. Right? So you put in delta x, then, getting more specific, you put in the function. In this case, the function is 3x plus 4. So if I plug in the function, I'm looking at 4 over n and 3 blank plus 1. And in that blank, I'm always going to put some multiple of ith 4 over n. I'm always going to put one of these guys into the function and find the height. Okay. Now here's where we try and get, instead of this big summation-y thing, we will try and work towards putting a formula in for the I. We have all these formulas for the sum of I, or I squared, or I cubed, and we want to get to the place where we have just summation of I. Okay? So at this point, you're trying to isolate to get to this. Now, you're going to do a little bit of algebra. First thing we could do is distribute. And if I distribute, I would get 4 times 3, 4 over n, times 3, times the ith 4 over n, and then I'd get 4 over n when I distribute. Do you see? Now I can isolate this guy's I by just the counter is for the I. All the other stuff is not really related to the I, so I can pull all this other junk out front of the summation. So I can pull 4 times 3 times 4, which is 48, over n squared, out of the summation. And likewise, I can say instead of the sum of each of these sums separately, I could find or separate the sigmas, and I could say plus the sum of all these 4 over n's. Still, please stop me. I don't understand. This is kind of funny. So if you're not clear, say, hey, where did you do that? Please, I beg you. Yes?
So the I is just basically saying it starts at 1.
Right, exactly. Yes, it's counting. I is really counting up what x value you're putting into the function. So when I equals 1, then the x you're putting into the function is a single 4 over n. When I equals 2, then the x you're putting in is the second 4 over n. So yeah, I serves as the counter that you're putting in as you go. Yeah? All right. This. Now this, you look at this fancy summation, it's so scary, but when you see this, you should have in the back of your mind, this just means 1 plus 2 plus 3 plus 4, blah, 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 plus up to n. Now, that's kind of hard to figure out what that would add to, 1 plus 2 plus 3 plus 4 up to n, but there's a formula for it. The formula is that the sum of 1 through n can be found by that formula, which is the arithmetic series formula. It comes from the pairing the rainbow constant. You with me? All right, cool. This, you could pull 4 over n out front and just call it adding 1 to itself over and over again. Or you could think of it this way. 4 over n plus 4 over n plus 4 over n plus 4 over n times. How much would that come to? 4 over n added to itself n times. 4 over n times 4 over n times n, or just 4. Okay? Now you could, another way to look at this, let me maybe say it this way. I don't know if that, let's say I pulled that out instead. Okay? I said earlier that you can pull an n term out front of the summation, and that's allowed. Okay? Because the counter is just about I. Again, this looks fancy, but it just means add 1 over and over and over. How many times? N times. What's 1 added to itself n times? N. So this then, at the end of the day, is 48 over n squared plus 4 over n times n. How are you doing on room here? Do you have anywhere close to enough? Can you go out to the side and finish this? I'm just curious how much room this is taking. All right. Now, do you have any idea what the heck that does? Great. You did all this math. What is it? Oh, I lost the formula. Good point. It didn't go anywhere. It's still there. Thank you. Okay, it's still there. I apologize. I messed up. Okay. So what is this formula? I'll call it A. It finds what? The area under the curve by using what? A rectangle. So if I used 2 rectangles, this would give me an area estimate here using 2 right-hand rectangles, right? And would that be good area or not quite exact? Not quite exact. What if I use 4 rectangles? A little better? Okay. So the idea is that one of the core ideas is the more rectangles, the better the fit. So in order to get perfect fit, we will then take the number of rectangles to infinity. If I take the infinite limit on this formula for this area rectangle estimate, surely there's a million cleanups we could do there, but you're doing n behavior. In n behavior, just worry about the greatest power. So for example, this first guy, it would be 48n squared over 2n squared, so roughly just 48 over 2. And the other one, the n's would drop out, and that would just be 4. So what's the area? I'll finish it up for you, don't worry. I get 28. How about you? All right then. Tell me, my friends, is there, now you might, if you really have your eyes open, you might say, did I really have to do all that rectangle stuff? Because isn't that shape, the area under the curve, just a trapezoid? Could I have just found it trapezoid-wise? And the answer is, yeah, you could. That's not always there for like parabolas and stuff, but it serves as a useful check. If I check by trapezoid, base 1 plus base 2 times height divided by 2, the bases would be the function, the parallel. Remember, the bases aren't necessarily what's horizontal, it's what's parallel, right? So what's the first base? At 0, the function is 1. What about base 2? At 4, the function is 13. What's the height, or the parallel perpendicular distance between the bases? 4. I get something like 14 times 2, or 28. We're good. Okay? That's the process. You start with the basic Ham summing base times heights. You plug in the delta x. You plug in the function. You clean up to get I by itself. You replace I with a formula. You take the limit. Okay? Try it on your own. Yes. The formula for the sum of I squareds I should have provided you with. I will provide you with these formulas. Sum of I squareds is this. I will always give you those. how we do here. Where are you at in your work? Are you at the, you've replaced the summations stage, or you're still in the summations? Summation, still in summation, okay. Sorry, I don't expect you to go fast like I did. I've done literally hundreds of these. All right, so did you get, what did you get? 15. Okay. The top, it's very common that people forget that 2 over there. If you think, if I distributed it all out, what would the greatest power term be? It would be 27n squared times 2n. It'd be 54n cubed over 6n cubed plus 6. So that's where they're getting 15. Make sure you don't lose that 2. That happens a lot. All right? Well, that'll get better. We'll gradually get that mastered. And let's move on to yield notes. This should take too long, I hope. First of all, do you know the 3 definitions of the derivative, back and forth? All of them have the big idea of change between 2 points or slope between 2 points and taking the points close together. That is the notion on all 3 derivatives. All right. So if you get a limit problem on the AP test, there are probably 2 of these on the multiple choice. It's important that you recognize when it's a real limit problem, when it's a definition of the derivative limit problem. And if it's a definition of the derivative limit problem, then you're expected to use derivative rules to do it. So would you try these 3 multiple choices? And there is 0 reason you shouldn't go 3 for 3 on these bad boys. Go. File, there it is. Right? Or 1 more minute. Let's say yes, you're ready. What do you think of the first one? What do you see that? What do you think? Which definition of the derivative is it? It's the first definition of the derivative. Okay? At a point or generally speaking? at a point. So what is the function? This says this is say, hey, what's the derivative at 8 or 2? Oops. 8. Ouch. Messed it up. Okay, and what's the function? Cube root of x. Okay, at 8. So after you've identified what's the function, you actually take the derivative. The derivative is 1/3 x to the negative 2/3. Or if you like, 1/3 cube roots of x all squared. So at 8 then, if I did this at 8, what do you get? 1/3, what's the cube root of 8? 2 squared, 4 times 3. Oh, did you get 112? Okay, good. This then, also first definition, what's the function? X to the 5th at a point or specifically, or at general, sorry. At 2 or 32? 2, okay. What is f? Oh, actually that's enough, never mind. So, looking at your answer then, what did you choose? D, yes, I agree, D. Wait, okay? All right, and finally, the derivative at 1 can be found a lot of ways. This is a question going to that. Does the first one find you the slope at 1? It is so close, and I was thinking yes, but I didn't look at where the problem was. Where's the problem? Yeah, this is supposed to be f of 1 plus h minus f at 1 over h. That is bad. So that is a no. Okay, what about the next one? Yes or no? That is the alternate definition. I would maybe even just write the alternate definition on the side and see if it compares favorably, and it does. How about the last one? Yes or no? Yeah, this is just a mess. That's like the first definition of the derivative at a point, generally at any x, but then this, what is that? That doesn't even. That's just crazy. No. So it is B. Okay. Those with practice can be gimme questions. Hopefully, we'll practice those a lot. Definitions of the derivative are often used to prove in mathematics. They are a theorem, and as such, they prove. But first, a bit of a review. It's been a little while since I went back to this. What are the 3 reasons a function might not be differentiable? Sharp turn, which could be a corner of a cusp. What else? What? Vertical tangent? Vertical tangent or vertical asymptote? Vertical tangent. And what's the last? Any kind of discontinuity, yeah. Okay, you cannot have a derivative at a point that doesn't exist. You must have continuity to have differentiability. So, with that said, does continuity imply differentiability or the other way around? If it's continuous, then it must be differentiable? Not necessarily, because it could have a sharp turn or a vertical tangent. If it's differentiable, must it be continuous? Yes, okay, so does continuity imply that's a no? Its differentiability implies continuity. Okay, now then, you should be able to do A. Would you please, first of all, change yours? I think yours says something about e to the x minus 1 plus 1, something like that. Scratch that and change it to this, because I forgot you do not know L'Hopital's rule. Apologize. You probably weren't able to do. So change it to x1 minus x cubed. Then, would you please show that the function is continuous at x equal -1? Using the definition, which means you should have limits of plenty in your work question. Okay. Catch up to you here. It's continuous if the limit as x goes to -1 exists, f at -1 exists, and they are the same, yeah? Okay. The limit on a piecewise, the limit will only exist if the one-sided limits are the same, yeah? So did you show something like the left-sided limit is 2, and that's equal to the right-sided limit, which is 2. Did you also say that f at -1 exists and is 2? Because they are equal, the limit as x goes to -1 is f at -1. F is continuous at -1. We? Okay, now the hard part. The hard part. What's going on with this? That's why. Okay, boom. So first of all, I would like you to get a picture so you understand what the heck is going on here. If I were to graph this, I know they both meet at -1, 2. Okay? The parabola is used on the left-hand side. Now the parabola, if I graph the whole thing, would look like this, yeah? But we're only graphing from -1 on down. So that's the parabola x squared plus 1. 1 minus x cubed, I know x cubed looks like this. Negative x cubed looks like this. And 1 minus x cubed then would be shifted up a little. So in terms of the x cubed, I'm thinking it looks something like this. You follow? Okay. Now, we're going to show that the derivative doesn't exist there. This is pretty nebulous. If I zoomed in on that, would it look smooth? Is there a sharp turn there? It's pretty close to smooth. Hard to say visually. But the idea is we're going to show that if this, the idea on the definition of the derivative is if I take the point at -1 and some point other on the curve, draw the slopes between them, and then get the points closer and closer together, that's the derivative, right? Now, what the slopes approach on the left supposed to equal what the slopes between -1 and some point on this side would have to be as they approach. If those slopes don't approach the same slope, then the derivative all breaks down and the derivative doesn't exist there. That's where we're headed conceptually. Are you with me? The left-hand side then is to say the limit as x goes to, now x is some other point on the curve. So x is going to approach -1, and it's on the left side of -1, so it's approaching from below. I'm calculating what happens to the slopes. What's the slopes, or the alternate definition here? F of x minus f at -1. That's the rise between the point at x and the point at -1 over the run x minus -1. Okay? Now, if I am working from the left-hand side, then I have to use the left-hand f of x. The function I use for the left-hand side is x squared plus 1. What is f at -1 from our previous work? We know that needs to be, or is, 2, yeah? Are you with me? Okay. Now, upon direct substitution, you'll see 0 over 0, which is common. That's how the derivative works. It's a small change in y over small change in x. It should always come out 0 over 0. But we can do some algebra. if I call this x squared minus 1 over x plus 1, well then I can factor. And the x plus 1 would drop away. And it would become the limit as x goes to negative 1 of x minus 1, which is negative 2. What does negative 2 represent over here on the graph? It's what the slopes on the left approach as I get closer and closer. These slopes are approaching negative 2 as the parabola approaches negative 1. You with me? Okay. Would you now try the same thing about the slopes on the right? What about when you draw slopes between negative 1 and some point on the right of the piecewise? Try that on your own and let's see what we get. Here's where we see if you remember your factoring of cubes. And the answer is yes. Oops, this should be plus 1. How does x cubed plus 1 factor? X plus 1, x squared minus x plus 1. Same opposite positive for the same signs. Okay, so at that then you can, after the x plus 1 drops out, you can substitute and solve negative. What do we got there when you put a negative 1 in? 1 plus 1 plus 1, so negative 3. Although it's close, the slopes from the left are approaching negative 2, and the slopes from the right are approaching negative 3. And if you zoomed in hard on that, it would be a really sharp turn. Did I make a mistake?
Like take down 2. Where did that go?
I combined the 1 with the 2, and I got 1 minus 2. That's where that came from. Yeah. Sorry, I didn't make that clear. All right, so because these are not equal, the limit at negative 1 doesn't exist. Are you tracking? That's how you would prove not differentiable. Yes?
I believe the function was g of x to begin with.
Oh, darn it. Good point. Phew, I only did that once. Thank you so much. I had actually put that in thinking I'm going to make sure they pay attention to the name of the function, and then I did. Thank you. I'm glad you mentioned that. And that, in a lot of cases on the AP test, that cost you. Thank you. That's done. Not me. All right. Good call. Anything else on this, real quick? Okay. Chain rule. And we've done chain rule in a more simplified version, but I need you to recall the chain rule beginnings or the domino effect, all right? So look at this here. You have y as a function of u is a function of v, and v is a function of x. If I asked you to find dy dx in terms of x, then you could do a ton of substituting in. You could put this in for v and that in for u and make a y-x equation. The problem is that would be such a stinking mess. It would be the sign of that with those in place. It would be terrible. Right? So sometimes it behooves you to leave it apart and use the chain rule. You could say, or you could find dy du, because that would be an easy derivative. On the next equation, you could differentiate, and when you took the derivative in Leibniz notation, what would it be? du dv. And that third, if you differentiate it in Leibniz notation, it would be dv dx. Well, if you then multiplied all through 3, then d's, or they go away, and dv's go away, and you have dy dx. Now that is the chain rule. Y relates to u relates to v relates to x. So in a indefinite or non-direct way, they relate to each other. So that's the plan. What's dy du? What is dy du? Cosine of v. What's du dv?
To B plus 3.
2v plus 2. And dv dx, I just had to get a little quotient rule action in there. What's the quotient rule as applied to dv or v? Low, oh, you're right. Low, 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 d high, 1 minus high, below. Over the square, oh, what's below? What's e to the x all squared? Same as e to the 2x, yeah? All right, now that's great. The question that did say find dy dx in terms of x only. So I want to substitute in. Let's start with subbing in for u. What is u? What can I put in place of u? V squared plus 3v. Now I've taken a step forward because now instead of 3 variables, I got it down to 2, x and v. Now I'm going to take another step forward and get rid of v. What can I put in place of every v? X over e to the x. Okay, so cosine of x over e to the x squared plus 3 x over e to the x times a quantity 2 x over e to the x plus 3. I'd be astonished if I can make this happen. E to the x minus x e to the x over e to the 2x. Boom. Now you can imagine how ugly that must have been if I'd done substitution back and made a single yx function. It would have been pretty hairy to come up with something like that. So that's chain rule by gradually relating y to x through a lot of in-between steps. Try one on your own. Try that guy. If you're not clear on how to go about that or start, let me know. If you get something like that. Do we agree? Why are you so slow? Come on. Let's go. How are we doing? Do you at this point, is it just, yeah, I'll copy it down, or would you get there? Slowly. Is it because you're slow thinkers or because you don't have faith and you're constantly asking, is that right? Is that right? It's real. All right. I don't want to rush you. I want you to do it well, but for Pete's sake, we got questions to go through. Yes, sir.
It's like part of that.
That? Yes. That's good. Thank you. Okay. All right. I do have an error. You're right. Okay. Chain rule application, word problem style, and then we'll be good. This actually does happen in real life. You might think this is so nebulous and abstract that it has no applications, but this happens every time you drive a car. Your car doesn't always get the same gas mileage. That's ridiculous. You get better gas mileage at different speeds, or if you're on a load, on a hill, something like that. So, say your gas mileage was a function of your velocity. These are made up by me. This is not actual scientific modeling. I just kind of made it up in the fly. But if you have gas mileage as a function of velocity, look, something like that, where the mileage is in miles per hour and velocity is miles per hour, miles per gallon and miles per hour. And then that was based on some guy's car, okay? And then Joe, who owns that kind of car, took a trip, and his velocity was that kind of function, okay? V is in miles per hour, and time is in minutes, how fast he is going at different times along his journey. If I asked you for his gas mileage at time 7 minutes, now I know that you don't have this. This is actually the question that got cut off the paper here. So we'll add that in a second. But let's start with question A. Joe's gas mileage at time 7 minutes. What would you do? Okay. Could you find, does mileage depend on minutes? His time. Does mileage depend on time? No, it doesn't. It depends on velocity. See, it's got V in it. Okay. What does depend on time? Velocity. Okay. So I could start talking to him. How would you go about this? At time 7, you could find his velocity and then use that velocity to find his mileage, right? Okay. So his velocity at time 7 is 8 plus natural log of 8 cosine 7, which would be approximately what? 8 plus natural log of 8 cosine 7. I'm thinking something like 9.567 miles per, what is that in units? Miles per hour. Okay, it's velocity. All right? I know how fast he's going at time 7. At time 7 seconds, he's going about 9.567 miles per hour. Now, how can I find his mileage at that point? That into V. I'm at a velocity of 9.567 would be 18 minus 6. I'm actually going to store this to A, something like that. The mileage at that velocity, is 18 minus 6 cosine of pi times A minus 90. So 18 minus 6 cosine of pi times that answer minus 90. 23.8105? Is that what you got? And what are the units on that? Miles per gallon. At that instant, he's getting roughly 23 miles per gallon, 24 miles per gallon. Okay? Now that is a pre-calculus problem. That's not a calculus problem. Calculus problem is his gas mileage increasing or decreasing at that point? That means you need to know, how do you find if something is increasing or decreasing? You need to know the sign of the derivative, right? You need to know, is m prime positive or negative to know if something's increasing or decreasing. Well, m prime, or let's call it dmd. Now that's as a function of time, so I need dm dt. Dm dt, but m and t aren't directly related. So by chain rule, I could find how mileage is changing with velocity, and then analyze how velocity is changing with time at time 7. And in the interest of time, I don't know if we have time to do that, but you could take the derivative either by hand or by calculator, evaluate it at 7, and that would be it. Okay? All right. That rectangle stuff took more time than I wanted. This, I expected it to take a while. But how are we doing on 42? Can we get 42 today, people? I say we can, because the key's not online, so yes, you'll turn in 42 today. These are replacement problems. Can I point you in the right direction on maybe one of those two? At least get one of those second derivative problems done. Yes? No? 21. Okay. 21. Let's try 21. And I wish I would have done it better or had an example of this in your notes, but get this now and it'll work. Okay. So let's start with, I think in your homework it might have said y double prime, but it's really the second derivative. Cool? Okay. Can't get to the second derivative until you take the first derivative. So we're going to take the first derivative, and you have 2x minus 2y dy dx, or if you like, y prime plus 2 dy dx equals 3. Therefore, the first derivative is dy dx is 3 minus 2x over negative y, 2y plus 2. Do you agree with my first derivative? Okay, that part shouldn't have been hard. That's not new. The new part is the second derivative. If I find y double, I need to take the derivative of that. Well, if I take the derivative of the left side, that's the second derivative, which you can use that notation or y double if you like this one. Okay? On the right side, you'll see a quotient rule. This happens quite a bit, where you get a second derivative that uses the quotient rule. By quotient rule, low, negative 2y plus 2. D high, what's D high? Negative 2 minus high, 3 minus 2x, put parentheses around it. Here's where D low comes. D low, what is it? Negative 2, you're taking derivative of a y term here, dy dx, over the square of what's below. Now, all that's great, but you're supposed to make it all in terms of x's and y's, so what's the last thing you have to do? You replace this with that. And if I had more room, I'd probably do it in the second step so as to make my work clear, but I've run out of room. You with me? So you get a dy dx and you sub for that dy dx, and that's going to happen implicitly. All right, that should get you going on 4 because it's the same notion. And then the critical number of my key has that. So make sure I get 42 today. 43 is not today, but 42 is. Also, 2 days before the test, so it's a good day to come in and start reviewing. Have a nice day.